Yeah. So, do we have any questions from last time? So, essentially, last class was just about, was basically about, we talked about Euclidean path integrals for gravity. So, which is conceptually there is a bit of a leap compared to the Euclidean path integrals that we talked about in quantum field theory, either in fixed backgrounds. Okay, so there is a conceptual leap because now it is somehow thought of as being defined in terms of asymptotic boundary data, and most of the there are two kinds of data that you have to specify. So one kind of data is the data related to, so there is a topology. So that's what we meant by the fact that there is a, so if you want to interpret this gravity path integral as a, in the standard way that we do in quantum field theory, where if you have a periodic time direction, this path integral is interpreted. If periodic Euclidean time direction, then you interpret that as a canonical partition function, right? So a similar thing, if you want to do it, it's a prescription of the topology of the boundary. And then there is also a notion of the length of the boundary is beta, etc. But then there is also another question that you could ask, which is to set up what are the boundary conditions for the various fields and then do path integrals. So these are all things one could do. Okay. So roughly speaking, the kind of data that one specifies at infinity are either like, you can think of them as P's or Q's very roughly. Okay, they are either configuration variables or canonical conjugates of them. So depending on this, we'll have different kinds of ensembles for gravity and so on and so forth. So this is like a, so because the point is that the fields that you're defining at infinity in gravity are what define your path integral basically. So this is, so that's the picture very roughly. So I'm kind of answering a question that was there last time. Even now, not in a very good way, but maybe slightly better than yesterday. Okay? So there was a question about what is the kind of things that you specify at infinity? So, and the things that you specify are roughly speaking the boundary values of fields. Their interpretations can change very roughly, So, the most important thing for us is this canonical ensemble where you declare it to be a periodicity in beta. So that's the one that matters most for us. Okay, so and assuming that there is a well-defined thermodynamic limit, the things that we calculate here will presumably be correct in any ensemble. So the change in ensemble will probably not matter. This is the hope. Okay, so now and after that what we talked about was we talked a little bit about so the Euclidean ADS-CFT. So first we set up Euclidean path integrals in gravity, then we set up the Euclidean ADS-CFT correspondence, which is the thing that, GKPW Witten correspondence is sort of the original ADS-CFT correspondence, if you like, between bulk and boundary. So essentially what we wrote down, I'll repeat that, in the most telegraphic way I'll repeat that today, which is that we say that this is our, so the CFT path integral with some specified sources. So path integrals are always specified with sources in quantum field theory. This is a field theory path integral. Okay? So this generating function, so this object when it is a source that is coupled to it, it is called a generating function. They are all path integrals of various types, but the point is that when you have a J0 as the source for a field theory guy, then that's what you specify. So essentially the ADS-CFT correspondence is saying that sources for the fields are what are fixed by the path integral in gravity. Okay, sources for the dual field theory fields are what one should think of as the boundary values of your fields in gravity side. So this is equal to set grav J0. So the notation seems kind of almost tautological, doesn't seem to contain any meaning, but the point is that, this gravity path integral is to be thought of as a definition in some asymptotically ADS geometry in which DM is a boundary. Okay, where the boundary values of your fields are fixed. Okay, so the boundary values of fields in the gravity description are just boundary values of certain classes of fields which we call non-normalizable fields in Euclidean signature. Okay, but in the CFT side, the same boundary values get interpreted as sources for the field theory. So this was the key point. So if you can, so the strategy that we will, for instance, what we'll do today is that we'll try to compute this quantity using gravitational methods. So as I said, this quantity is completely well defined if you have a Lagrangian like n equals 4 preambles, but it's very hard to do anything with, because even QCD we don't know really how to solve in a useful way, right? So, and this is a theory where we are really interested in understanding the thermal physics. Thermal strongly coupled, highly nonlinear, highly chaotic physics is what we are interested in, because that's what black hole physics is. So the place where we want to understand quantum gravity is in the context of black holes, and that's the most difficult part of the field theory. But there exists some kind of an approximation that seems to be happening in the gravitational description, where we might be able to compute it approximately. But the problem with the right hand side is that this is only, we know how to do anything with it only in the semi-classical Euclidean gravity kind of limit. But so it's clearly not a complete definition. It is some sort of an approximate definition, but that approximate definition we know how to calculate here. So we do that to calculate this and then make some statements about what happens in the gauge theory and find, let's say, whether at least qualitative features are parallel, etc., etc. So this is the kind of thing that we want to do. Okay, and we are going to take a space-time which is the boundary space-time. We will take to be basically some kind of s cubed times r. Sorry, s cubed times s1. Well, s cubed. Let me just take it to be s cubed. Or dm is a space-time, so let me write it s1 times beta. Okay, so there is a periodic circle. So essentially what I'm working with is the thing that I'm imagining is the boundary of ADS, where this guy is the S3, the sphere, and then I'm imagining that this guy is beta periodicity, and I've identified it so that it is thermal. Okay, so that's the boundary on which my CFT is living. Okay, and so yeah, so in order to specify that the ADS radius is L, I'll sometimes write it like this. Yeah, so this is the Euclidean cylinder with periodic identification, and this beta is, beta captures the temperature at which we are setting the theory. So the system, the ensemble or the theory that we are going to consider is defined by that temperature. Okay, so that's where we are defining the temperature. And now we are going to try and calculate things in the gravitational side using this Euclidean path integral kind of setup. So we did that Euclidean path integral calculation in flat space. Okay, and we computed the partition function, the canonical partition function for a Schwarzschild black hole, because Schwarzschild black hole is really the only thing that was there. Okay, so I mean you could consider, so of course we are also assuming that this is the only solution that exists with this particular symmetry is this Schwarzschild black hole. Okay, you could consider like rotating black holes and so on, but rotating black holes, for instance, you'll have to specify some other, you'll have to define something like a grand canonical type of ensemble, where there is, or where there is some, potential for the angular momentum that you're specifying. So like something like, some omega or something. Okay, so when we are working in the canonical ensemble where we are only specifying beta, Schwarzschild black holes are sort of the natural things that you might consider. So, so here now we are going to go and look at the gravity side where if everything is in ADS, and the claim is that we want, so this is the kind of space-times that we mean by asymptotically ADS, at least in the, if you're really thinking about, this is the asymptotically ADS geometries that we're going to look at. Okay, so and these are nothing but, okay, this is in some form of Poincare type coordinate, and we are going to simplify things by just considering the case where only the gravity or the metric is turned on. Okay, so we don't expect that because black holes have so much entropy, we expect that in any configuration where black holes are important, at least we will see. I mean, this will become clear only sort of hindsight a bit, that the dominant physics is going to be controlled by the gravitational physics and not through the, let's say, the bulk fields that might be there, let's scalars or form fields or whatever that you have in your original theory. So and the one rationale for thinking it a priori is that like black holes have a lot of entropy, and though other things generally speaking cannot contribute that much, let's believe at least. So and you will see that this is a reasonable assumption. Okay. Yeah. Yeah, so I mean this is asymptotically, I'm just defining, I mean I've written it before, but I'm just saying that this is roughly the kind of space-times that we're interested in. And the point is that with these boundary conditions, we are trying to integrate the path integral in some way. Okay, so it should be very much emphasized that this partition on the right hand side is not a completely, we don't fully understand how to give it a fully satisfactory definition, but at least in regimes where we expect that the boundary, conformal field theories have, we know all the, so because we know the conformal field theory, we expect that we know all the operators of the conformal field theory. So then it is natural to think of sources that couple to those conformal field theories, and the idea is that the bulk path integral is defined in terms of them, and that's what we are hoping, okay? And we are going to just turn on some fields in the CFT, some low-lying fields. For example, if we are just turning on the metric on this side, on that side, that corresponds to just turning on, roughly speaking, stress tensor. Okay, so that's we are only being interested, not turning on so much. That's what we'll be interested in. Okay, so okay, so now we want to compute. So we want to sort of repeat what we did last time for pure ADS. Okay, no fields other than standard ADS, gravity. So 12 by L square is the standard normalization for, in 5 dimensions for the cosmological constant. Okay, so this is our action, and like last time, we want to introduce a boundary term, a Gibbons-Hawking term, and also a counter term to make things finite. Because here also r going to infinity, you will end up finding divergences. Okay, so the volume of space-time at infinity in ADS is still infinite. I think I mentioned this, right? So even though it is, in some sense, it's a finite distance away, but what that really means is the time it takes to send signals and get it back is finite. But that's not the same thing as saying that the volume is finite. The volume is infinite. So you will have to diverge, carry this regularization. Yeah, so the point is that, so the idea is from last time what we were saying was that the partition functions or the free energies, okay? So if you compute these partition functions, the things that you get are basically what we are calling beta times f, or the free energy. This is roughly what we were talking about last time, or minus beta f, okay? Right, so is that correct? So maybe the sign is correct or no? Did I write it somewhere? This is the reason why it is better to give like prepared these notes a couple of days ago. So now I forget the various choices that I have made. It's better to give the talk right fresh so that the calculation they've done is like fresh in your mind. So it's a minor thing, but well, we'll deal with it when we get to it. Okay, so the idea basically is that you have these calculations, these actions basically will fix the free energy for configurations, and the idea is that we want to look at the configurations with minimum free energy as dominating the canonical ensemble. So let's say you can compute, so at any given temperature beta, we will see that there are 3 kinds of solutions. One is the empty ADS solution, then there is what is called a large ADS black hole, and then there is a small ADS black hole. Okay, so and they are basically characterized by the fact that their horizon radii are bigger than the ADS length scale or smaller than the ADS length scale. So given a beta, there are 2 such solutions. This is different from flat space. Okay, so and then the question is, which of these is going to be having the least amount of free energy or the least amount of action? That is the thing that we are going to be interested in. Okay, so
f is log of z.
Yes.
So it is an exponential.
Yeah, so that's where this beta is coming from. But I'm a little confused about so e to the minus, what is it? E to the minus IE is log of is z, right? So, but the point is, so this is not quite it. This is what is true. So I think when you take a log z, it basically, there should be a beta somehow I have to extract. This is what I remember. Okay, so but anyway, so we'll fix it. Let's not waste time on it because we'll fix it when I have to fix it. Okay, so yeah, so this is, anyway, the thing that we want to minimize is the action, and it's related to the free energy by a beta, which we will figure out as we proceed. I mean, we can fix it by looking at thermodynamic formulas and so on, but my knowledge of these things is always sketchy. So, okay, so let's write down the general, so it's easy to find, the Einstein equation that you get from it, you can easily solve using spherically symmetric ansatz, just like in Schwarzschild and so on. So and the key point is that we are interested in solving this kind of solutions exist, and you can explicitly find, and in fact there exists a Birkhoff-like theorem even here, that this is the form that you have. Okay, so this is the solution for Schwarzschild, And so there is, implicitly understood here is the boundary condition that we are imposed, that is tau going to tau plus beta. So this is part of our assumption. And note that this is d omega 3 square because I'm working with ADS 5. I want to make an interpretation about the dual gauge theory, which is in 4 dimensions. Okay, so I'm working with 5-dimensional theory. So, but the statement is not particularly different in other dimensions also. Okay, as long as you have conformal field theories on the other side. Okay, so this is essentially d theta 1 square plus sine square theta 1 d omega 2 square. So, and so this is a polar angle. This theta 1 is, going from 0 to pi. So if you have any sphere, you can parameterize with a set of polar angles. So you take a small S1, you put, you can make an S1 with the d theta 1 square plus sine square theta d phi 1 square, d phi square, and then you can keep doing that to more and more polar angles which are ranged from 0 to pi, and you can construct any n sphere. Okay, so that's the standard metric that we'll use. So this is what we have here. And so the point is that the horizon is basically defined as the highest root of this, the most positive, the biggest root of this guy. This is the outer horizon. Okay, so and it always, not just here, in any space-time, the outer horizon of a black hole is basically the biggest root of this, what is called the blackening factor. Okay, that's always the definition. So here it's easy. You can actually, so many cases you will not be able to solve it exactly, but here you will actually be able to solve it. For instance, if it was r cube here, okay, you would not be able to solve it, in a nice way, at least, What is that?
Where is the mass of that?
This mu is controlling the mass of the black hole. So it turns out that the mass parameter in the solution need not be directly the actual Hamiltonian mass of the space-time. So in ADS, it's actually, there is some factors. We'll eventually write it. So if you compute the energy of this in this canonical ensemble calculation, what you get is actually the ADM sort of mass that one can define for this, and it's not quite new, but it controls it basically. So this mu is so it's you can think of it as a mass parameter, even though not quite the mass. So and then you have a formula like this for the horizon of the black hole. So this is my r plus, the outer horizon or horizon here. So, and it's bigger, it's real, positive, etc. You can check, and also we also need to understand how the r plus is connected to the beta by this regularity requirement, right? So we can do the same conical deficit kind of thing, completely straightforward, and this is an important formula, which is that you have. Okay, so this is the formula that you get, and you can check that. You can do various things. So this is, I think it's this is correct. Yeah, I think it's correct. Yeah, it's correct. Yeah, so and then you can also write. Some of these formulas will be important. Right now I'll explain why these formulas are interesting or important, which is that. Okay, so there is some formula for the r plus in terms of the beta, because that's what is somehow fundamentally important or interesting if we are fixing beta and defining the theory using that. Okay, we are not interested in expressing the beta in terms of r plus so much, but we are interested in expressing r plus in terms of beta, because once you fix the beta, the regularity condition is going to fix the radius of the black hole for you. Okay, so this is the result, and the key result is that key observation is basically that the formula itself is not very important, but it has two solutions. Okay, and one of them, the radius r plus, is smaller than the other. And so that's the origin of the term, small versus large ADS black hole. Okay, and the small black hole, as we will find out, it will have, thermodynamically it is not important. Okay, so so from these expressions you can see that beta has a max value. So beta max is equal to L pi by root 2.
What do you mean by thermodynamically not?
We'll see that in a second. So thermodynamically not important essentially means that its free energy will always be higher than that of the large black hole. The large black hole is lower free energy. Yeah, so it's also kind of understandable because, I mean, see, small black hole, if you look at this and play around with it and kind of look at it a little bit, you'll see that it is basically, the horizon size is smaller than that of ADS length scale, very roughly. That's what you'll see. And the other guy is bigger than ADS length scale. So what it really is saying is that, so when the black hole's radius is less than the horizon, the curvature scale of ADS, it's roughly like a flat space black hole. And flat space black hole will always evaporate. You know what I'm saying? So that's why, for instance, we did not compare the free energy or anything like that. So the free energy is, we did not really do much of a comparison of anything in flat space, basically because the black hole object that is sitting there is unstable. So it is, in some sense, it is never going to dominate the ensemble. Okay, so we computed some things, but we did not really, so it's only like interesting as, its complete interpretation is still not clear in some ways. But here we will be able to make a clean interpretation because the dominant phase is the large black hole, and you can clearly interpret it in terms of this canonical ensemble type of calculation. Okay, it has a good interpretation in the canonical ensemble. Okay, so beta has a max value, basically means that there is a low temperature. There is a temperature above which only these solutions exist. Okay, so yeah. So, of course you also should note that, if I just set mu equal to 0 here, that's always an acceptable solution of this equation of motion, right? So that's called thermal ADS. We'll talk about it a little bit. So that solution always exists. Okay. So, and the competition in some sense is between the large ADS black hole and the thermal or empty ADS. Okay. So, yeah. So the competition, the free energy competition is between these two things, and the sort of the punchline of today's lecture is that on the gravitational side we can see a phase transition. So the dominant phase changes as you tune the temperature beta. So, as the temperature becomes large, the large ADS black hole becomes the favored phase, and below that temperature, the empty ADS, or empty ADS, more precisely thermal ADS, thermal ADS means ADS with a periodicity in tau. Okay, so yeah, so that will become the dominant phase. So, and that phase transition is something that Hawking and Page had computed long ago, back in I think in 1970s or 80s. So long ago, completely for, so that's another great example of, somehow, like the fact that things were better defined in ADS was noted long before ADS CFT. And the recognition that this transition, this Hawking-Page transition is a nice interpretation in terms of the gauge theory was the thing that Witten noticed after ADS CFT. So, okay, this is one reason. So today's calculation is one reason why we believe, for instance, that a black hole should really be understood should be understood in the gauge theory. This is ADS CFT is not just about the ground state of ADS. You know what I'm saying? So the ground state ADS is where most of the symmetries etc. are manifest. You can say various things. So maybe it is just a way of incorporating the symmetries of the gauge theory around the ground state of around ADS where the symmetries are manifest. One could have taken that interpretation. But I don't think that is the correct interpretation. The correct interpretation is that N equals to super MLC is a theory of quantum gravity, because these calculations, you will see this and related calculations really are telling you that black holes in the bulk do seem to have a very natural interpretation in the gauge theory side. Okay, so, and there are many other things, but I'm just saying, I'm emphasizing one. Okay, so yeah, so and the second observation is that for any t greater than t min, okay, so when b greater than beta max means there is a t min. So there exists t min. That's what it means. Okay. So okay, let me write one more small formula here. So this happens at some particular r plus, which is equal to L by root 2. Okay, so if you plug in this beta into here, you will find that L by root 2 is a horizon radius. Okay, so for any t greater than t min, that is beta less than beta max, there exist two black holes. So there is one with R plus greater than R star, which is called the large AdS black hole, and R plus less than R star, which is small AdS black hole. Okay, so this is the sort of the picture, and yeah, so right. Okay, so let me make a comment. I already said this once. In flat space, larger black holes always have lower temperature, right? So this is, if you just, you can, so so if you take the T here, if you make it T, the L becomes downstairs, right? So then you can take L to infinity or 0 or whatever, L to infinity. Okay, and then you will find that, you can take L to infinity here itself right away. So then you will find that there is a beta is 2 pi R plus, right? So that is basically telling you that the temperature of the black hole, flat space black hole, is actually smaller and smaller as the radius increases and becomes bigger and bigger. So that means that, that means that by radiating, the black hole becomes smaller, but it becomes hotter. So hotter basically means it's radiating more. That's the literal definition of hotness. Temperature is a measure of how much it is radiating. Okay? So that means that once it starts radiating, or once the black hole has formed, it'll keep radiating until everything evaporates away. So that's why flat space black holes do evaporate away, and there is no, in some sense they are not, they will never be a dominant phase in the canonical ensemble. Okay, so I think I've mentioned this before. The radiation that forms that is left at the end of the evaporation is the really, that is more like the typical state in the Hilbert space. Okay, so specific heat. So another statement is that specific heat of, so most of the physics of small black holes is in many ways is similar to that of flat space black holes. Essentially because the length scale L is not relevant. That's what it really means. Okay, so similarly you can check that the specific heat dm by dt is less than 0 for small black holes as well as this thing. That's another feature of this, what I just told you, which is that if the mass increases, the black hole becomes cooler. Okay, so that's not really the way in which, so for large black, for small black holes. So if the mass, I said it the other way, mass decreases, the temperature increases. Okay, so and that's what specific heat means. Specific heat, negative specific heat means precisely that. Okay, so so large AdS black holes, therefore,
Is it for large black holes?
No, this is for small black hole. So positive specific heat basically means that if you pump energy into the system, its energy increases, its mass increases. Okay, so or if you add, or more correctly, I think it is better to think of it as if you maybe it's easier to think of when it's radiating. So if you have a object which is at some finite temperature and it radiates, it cools down. That's what positive specific heat means. So this is not the case here. Okay, so so wanted to say something. So the second point is that this means that we can, this is in some ways it's an interesting fact that the large AdS black hole is different, it's stable, all of that is good in some ways, because it means that those states can really be identified in terms of eigenstates of the CFT. Okay, if you understand, so we don't have to really worry about, so the fact that the small black hole forms and evaporates is a statement that it's a time dependent state in the CFT. It's much harder to study typically, we would imagine. But possibly for the large black hole, we may be able to understand it by studying eigenstates or the high-lying part of the spectrum of the CFT. Okay, this is one thing that we can hope. So, but also it means, so that's where we can make progress, but you also have to be careful in drawing conclusions about the small black hole or the flat space black hole by looking at these large AdS black holes, because they are somehow different in some fundamental way. Okay, so it's not completely clear, for instance. So it's generally believed, I would say that the consensus now at the moment is that evaporating black holes have smooth horizons. But on the other hand, it may be the case that eternal black holes, which are typical states in the CFT, they may not have smooth horizons. So this is, I would say that this is where, the current consensus is. I mean, it's, I don't know whether it has reached quite the place of, this is at least the dominant story, okay? I don't know whether it has completely reached the place of consensus, but this is what I think is generally believed. Okay, so some people disagree with it, but I'm just talking about what the dominant narrative at the moment is. So, okay, so now we can just calculate, okay? So we had all these, we did all the hard work last time in order to compute our, what was that thing? This Gibbons-Hawking term. So let's write down our action now. Minus, so the same kind of thing, except now we are working in so I'm putting a cutoff. So this is the induced metric that we had last time, and similarly we also have okay, so this gamma, so my gamma and R are kind of hard to distinguish. So this is R, and I think in this equation, this only here and here we have the R. All these other guys are gammas. Okay, so the gamma is basically the induced metric on the cutoff surface, and I'm calling cutoff surface R equal to 1 by epsilon. Okay, so last time I called it R equals capital R, but now I'm calling it R equal to 1 by epsilon. Okay, so, right, yeah, so, and this is, this is essentially because we think of this as a short distance kind of divergence in the dual CFT. That's roughly the reason. And this gamma is induced metric. So the point is, so the first term, so this guy I will call 1, and this guy I will call 2, and this guy I will call 3. Okay, so the calculation of 1 and 2 are very similar to flat space. There is not much of a difference. You just have to, the metric is a bit different. And one more thing that is a bit different is that because it is curved space, ADS is not, R is not 0. Okay, so you actually, this bulk piece will contribute. So unlike in flat space, the bulk, where bulk piece did not contribute. So this R, if you plug in for, from Einstein's equation following from that, you will find that R is minus 20 by L squared. Okay, so this gives me a bulk contribution, which if you write it out, so I'm writing this explicitly because I want to kind of explain. Okay. So this is just the volume of the 3 sphere, some some function of pi. Okay. And this integration is from R plus, which is the horizon. Okay. So because that's where the geometry caps off. Remember that these geometries are all basically of this form. Okay, so this is the beta direction and this is the R direction, and the claim is that we are making this point smooth by fixing the periodicity like this. Okay, so the beta fixes R plus in such a way that there is no singularity or conical defect there. So that's always the argument, so which means that, so note that topologically these are all disks. If you just look at tau and R, they are disks. Of course, there is other, phi's and so on, which are going around as well. But the crucial part for our discussion would be the tau and the R, and together they form a disk, topologically. So, and this integral is from, this is R plus, this is the location R plus, and this is 1 by epsilon. Okay, so that's where the integration is, and the tau integral is from 0 to beta, and nothing else is there. Okay, and this, if you do, you will find that this is so this is your answer from the bulk contribution. All right, so so now we can compute the second piece. Okay. Second piece is again exactly the same way as we did before, except the bulk, is different. The bulk metric is the ADS metric that I wrote down, ADS Schwarzschild metric that I wrote down. But other than that, there is no difference at all. So the result is okay. So I'm taking these calculations from Hartmann's lecture, so you can take a look at this in case I've made some typos or something like that. Okay, so these are, but he has done this calculation very cleanly. There's no, it should be completely accessible. Okay, so that's why I'm picking it from there. So and there are, this calculation has been done many times in the literature, but I think it's good to have one place to go and just look at it and all the notation, etc. Yeah.
So as the space consists of a terminus, there is nothing inside of there is nothing inside the horizon. There is no space.
See, it's like saying that what is beyond r equal to 0 in polar coordinates, right? So there is what is r equal to 0 beyond that, what is minus r? It's the same question. There is no meaning to that because it's basically we are putting coordinates on the disk. That's what we are really doing, right? We are saying that, so if you defined your new coordinate r minus r plus as some new coordinate, then the behavior of this would be, it's precisely like what happens in the origin of polar coordinates, right? R minus r plus is your, let's say some r tilde. So an r tilde equal to 0 is your origin there. Okay, so the question of, yeah, so like I think I answered this question once before. So if you can in principle analytically continue beyond r equal to 0 to r equal minus infinity, but then it will become a double cone there, this which has singularity at r equal to 0, which we don't want. So that's basically the conical defect that we are trying to avoid, essentially. Okay, so and it's kind of important in the context of Kruskal, if you remember, like because in the case of Kruskal, what happens is that, like if you are moving, going into r equals to 2m, that's not at the r equal to 0 point. Basically, there's a finite sphere into which you can fall. That's why you emerge on the other side of the universe, other side of the some other universe. So so here that's not possible. Okay, so. Right, and the third term is sort of the important term here. Third term is something that you may not have seen before, because third term, last time we just did some hocus pocus and subtracted following Hawking, what he did, right? So, but here we have like a very legitimate candidate, and I will explain what this is. So this is basically, so the purpose of this is still the same, which is to remove the divergent contribution coming from 1 by epsilon. It's still the same. So in that sense, it's conceptually analogous. But the difference is that now we are introducing this particular quantity which has a good interpretation in the CFT side. And this is, note that this expression is also, in some sense naturally covariant and so on. Okay, so, I mean, there are various counter terms one could introduce even in flat space, but nothing that is as satisfactory as this. So there are, there is, here I'm really definitively writing down a counter term, right? So there are, people have tried to do such things, but you will often find that you still need to subtract some kind of a background term. So this is what you usually find. So, but here, this, yeah, I mean, in fact, if you want a reference on flat space for doing similar things, you can take a look at Marolf and Mann. So they have some papers on, this background, this kind of counter terms at the boundary of flat space in some particular place. But I would not. So there are some ad hoc things that they still have to do. So, but here on the other hand, so this quantity is completely covariant. Covariant in the sense it is depends only on the metric on the screen, and you could in principle add more and more terms which are like higher derivative. But if the covariant number of terms that you can add are only a fine. They are all constructed in some sense from Riemann and Ricci and so on, constructed from gamma. But the point is that all the higher order terms, they do not contribute or help in removing the divergence that you get from adding 1 and 2. So the contribution, the piece, the removal of the divergence coming from this uniquely fixes this term. Okay, that's what makes this interesting. So, and this was done by, in this another famous paper, Balasubramanian and Krauss. Okay, so this counter term, you can go look there if you want. So the point is, but with this particular choice of counter term, the sum of all these three things that we have written down here is completely finite. Okay, and there is something a bit more natural than in flat space, I would say, because in flat space, as I said, this whole construction is a little bit, I have not found a completely satisfactory discussion. Okay, so with these, we can now write down the total action. So, and note that because we know that R gamma, this is just a direct calculation. There's nothing, this is actually simpler than computing the, what is it called? The K. K, because you have to first construct the normal, it's a bit of an annoyance. Here on the other hand, because we know the induced matrix by setting R equal to 1 by epsilon, that gamma is a trivial thing. So everything is, this is easy to compute. Okay? So, so the total IE is, so this is the form that you get. Some expression. Okay, and the key thing is that it is finite. So there is a unique way in which we could write down a covariant. So this, the thing that is nice about it is it's completely covariant on the induced metric on the screen. Okay, all the things that we have written down are somehow nice things. There is no background subtraction or weird things like that. So yes, and so the point is, so this manifestly finite expression, now you can use it to talk about what is, so the first observation that we will make is that, so this is an exercise. Okay, so IE R plus of small black hole. So I wrote down some beta expressions, maybe I should. Yeah, those expressions are important or interesting in that sense. So what we really want to do is we want to write this entire expression as a function of beta. Right? So, but the point is that this R plus is a function of beta and it has two roots. So this R plus will be, there will be, if you write R plus as a function of beta, you will find that it has, there are pluses or minuses will show up in this equation. Both will show up. So, and the question is, which of those leads to the higher IE? That's the question. So if you really think of this IE as a function of beta, the claim is that the beta for the small guy is greater than the beta for the large black hole. Okay? So is my notation clear? What I'm basically saying here is that you write this R plus in terms of beta, which is some formula that we wrote down. But it depends on, the R plus basically has two possible sign choices as a function of beta. And one of them corresponds to small black hole, one of them corresponds to large black hole. And what I'm saying is that if you think of IE as a function of beta, the small guy, the small sign choice, has a higher free energy or a higher action than this. So this is the dominant. Always getting confused about signs. So this I think is, this has to be like this. No, this is correct, right? So this is the one with the least action. Yeah, that's right. This is the dominant saddle. And there's a minus in the exponent, in the e to the minus IE. So this is the dominant saddle. So that's essentially the demonstration that in any, so we know that at any given beta, two of these solutions exist, and we have shown that this is always the dominant one. So basically for discussing the dominant phase in the canonical ensemble, we can just forget about the small black hole. That's what it means. Essentially because the small black hole will always evaporate away. So if you wait long enough. So, yeah. All right, so now we have, we can compute using our thermodynamic formulas what the entropy and the mass of these guys are, of the large black hole is. So I'm not writing this explicitly, these expressions, because they are a bit messy because of all the square roots. But it's easy to do, okay? So, okay, so energy, the formula is minus d beta log z. And so that gives me 3 pi square. This answers the question that we had, which is mu plus, I think it says an L square. Yeah. Okay, so this is our formula. So, and the idea here is that this, there is this overall coefficient is just, the parameter mu, how we define it. That's really what it is about. But this L square by 4 you can think of as coming from some sort of a Casimir energy because we are living on a sphere. This S3 is there. So it's not, so this is usually interpreted as a Casimir energy. So, because we are living in a bounded region. So the quantum fields themselves have some energy in it. Okay, so so that's what this is. So other than that, this mu basically is just the mass parameter. Okay, and so we can also compute entropy by using the standard formula. So this gives me pi square r plus cube by 2gn, which you can check is just a by 4gn. Okay. So both of these things we have gotten correctly. So, and this, by the way, you can in principle, in canonical general relativity, you can derive it independently by talking about charges at infinity, at ADS boundary and so on. So that matches with this calculation. Note that this calculation is a sort of a semi-classical calculation. It's different. It's not done by, at least superficially, it is not done by computing the charges of ADS in gravity or something like that. Okay. So that's the black hole part. So now we want to discuss the thermal ADS. Okay, so the goal of today's lecture is basically to talk about the phase, the trade-off in the phase space, the trade-off in the phases of the various solutions that we have. We already established that small black hole doesn't matter for any of this. So the only thing that matters is the large black hole versus thermal ADS. So let's write down thermal ADS. So this is the chalk in the other room is better. This chalk it's not getting me in the flow, so to speak. So dr square by 1 plus r square by L square, r square d omega 3 square. Okay, so this is our empty ADS. Our understanding is that tau has periodicity beta. Okay, and the exact same calculation we can do. There's nothing to really explain. You find that the total action, so the analog of this IE that I wrote here, so this is for BH and this is for thermal ADS, is equal to pi square beta some expression. So, and now the question is there a change in dominance of the phases? So the question is, we want to compare between the large ADS black hole and this guy and decide whether there is any statement that one can make regarding when they become dominant, which means who has lesser action or lesser free energy when we are talking about as we change the temperature. Okay. So this main key observation. So this is our first expression. So note this is 1 or A and this is B. So we are just comparing them. That's all we are doing. And the claim is that at beta crit is equal to 2 pi L by 3, or equivalently R plus crit is equal to L. The dominance shifts from thermal ADS to large ADS black hole. Large black hole. Okay? So that means that at T greater than T crit. Note that this T crit is different from the T that I wrote down where the black hole solution started existing. It's different. Okay? So this T greater than T crit, which is this guy, large ADS black hole, dominates the ensemble. So this was actually the observation made by Hawking and Page many years ago. Dominates the canonical ensemble. And so this, for this reason, it's now called the Hawking-Page transition. And it's a very important fact about this calculation that we are doing this calculation in global ADS. Okay, so global ADS is where there is a sphere at the boundary, and that's the reason why there is a possibility of a phase transition. So that'll become a little bit more clear, You could do the same calculation if you want in for instance, in Poincare patch. You can write down black hole solutions in Poincare patch as well. So, but when you do that, you will find that there is a sense in which everything, it's not comparable. It's more similar to a calculation in flat space. Okay? So, and I will explain why in a few minutes, why it is that way. So, but anyway, so the point is that on black holes on these asymptotically ADS global coordinates, which is what we have always been working on. So this omega 3 square is very important for our purposes. Okay. So for those, this Hawking-based, this phenomenon was observed by Hawking and Page long ago, and that's why it's called Hawking-based. And the reason why they wanted to work here is because you are working with a black hole in a box. Okay, but the moment you are in Poincare, the box interpretation of ADS is not that clear. Because it's a slice of the box, right? The Poincare wedge is a slice of the box, so it's not very clear whether you can really think of it as a box. So, and to really talk about phase transitions, especially if you really want, I did it in the canonical ensemble, but if you really want to give it a micro-canonical interpretation, the Poincare patch is not very good. Okay, Poincare patch has a feeling of an open system in some ways. Okay, so where are we? Yeah, so the next so the next thing we want to do is we want to kind of compute the entropy. So we want to give it some kind of, how do we understand that from the gauge theory? So this is our second question. So before doing that, let's try to compute what the entropy. So here we computed the energy and entropy and all that. Okay, so we can do a very similar calculation. The interesting object here to calculate is the entropy, because you will see that there is a huge jump in the entropy. So essentially, what is the structure here? Because this beta is just sitting there and R is just going, as just a free parameter, right? So this means that unlike the disk topology that we had, this is more like a cylinder topology. Okay, this R is sort of independent. There is no bulk point where the beta circle is shrinking down. Okay, so another way of saying the same thing, another consequence of that observation is that thermal ADS, if you compute the action, you can immediately see that it's just going to be beta times some quantity, which is not going to be the case, which was not the case, for instance, in our calculation there, because beta is non-trivially sort of fibered across the R direction. Okay, so here on the other hand, it's just a beta times whatever else is the R integral stuff and the phi integral stuff. So that means that we can compute it explicitly if you want, but it is clear that the action, this IE that we compute, is beta times something. Right? So which means in this formula, you will immediately get S equal to 0 for thermal ADS. Fine? Because beta will kill off this beta, that will be just 1, and then 1 minus 1 will give you 0. Okay? So because the claim is that this IE or the log Z is basically linear in beta. So then you automatically always will get this thing. So this is another important fact, which is that this absence of the conical defect in the bulk is essential for giving you finite entropy. So even in the Euclidean calculation, the horizon, the Euclidean horizon, where it just looks like the tip of the cigar is just becoming smooth, but that is very crucial for getting you entropy. Okay, the horizon even in Euclidean signature is essential for getting you entropy. So this means, yeah, but anyway, so at least at the 0th order, when you do this kind of calculation, you find that for thermal ADS the entropy is 0, but for Hawking, so for the large black hole or the black hole, both black holes in fact, you can compute the area to be this, or the entropy to be this. Okay, so right. So this statement here requires a minor caveat, and usually the way we think about it is that it's not quite 0. The way you think about thermal ADS is you have ADS ground state, but with some fluctuations which are non-back reacting on top of it. So those fluctuating modes are at some temperature T, or 1 by beta. So that's what one really should think about it this way. And if you actually, so in order to really talk about its entropy, we should really also talk about the loop corrections on top of the semi-classical contribution. So if you kept those in So the leading correction is basically at 1 over g Newton, right? So that's the leading thing that you would have gotten. The semi-classical calculation should have given you a 1 by g Newton thing. So the next guy would be an order g to the 0 result. Okay, so the real statement is that the entropy of the thermal ADS guy is not 0. It's 0 if you think of 1 by Gn as infinite. But if you were to look at finite Gn, this is the more correct statement. Okay, so and in our ADS CFT map between n and g and so on, this means that black holes have order n square entropy, and thermal ADS has order n to the 0 or 1. Okay, order 1 entropy. So this is what it means. Okay, so yeah, so this is so the general message. Note that this is a very general calculation. We have assumed hardly anything except the fact that we have ADS gravity. That's why Hawking and Page did it long ago. Okay, so it has nothing to do with really the details of many of the things. But if now, so this is just a property of gravity in ADS box, that's it. So, and if you now want to give it a holographic interpretation in terms of a gauge theory, then what this is really telling you is that, let me just write the statement so that theories with semi-classical, I've already mentioned it once, but now I'm making it more gravity duals or CFTs with semi-classical gravitational duals. Have a small number of states at low energy, and a very large number of states at high energies. Okay, this is what it really means. Okay, so essentially the energy and the so the idea here is that these guys at high energies are what we were, I already mentioned it as part of some qualitative discussion. Now this is really demonstrating it. Okay, that at high energies we basically have what the states responsible for this entropy on the CFT are basically what we call black hole microstates. Okay, so the holographic description of black hole microstates. Okay, so any questions? I mean, today's class, if you followed last class, should be kind of straightforward and simple. So, but if you have any questions, please do ask.
Thermal ADS is some sort of an empty ADS?
Yes, it's empty ADS. The words that people sometimes use is the, empty ADS with some gravitons gas, thermal gas of gravitons. The thermal gas of gravitons means, graviton should be understood in a sort of a general sense. Like for instance, if you have some low-lying scalar field fluctuations, these are also part of that count. So they are just basically saying that the scaling dimensions of the fields are those of those single trisect fluctuations around the vacuum. Okay, so those are what we were calling basically the scalar fields propagating in empty ADS, for instance, belong to that class. So ADS, the idea is that ADS you treat as kind of like as a fixed background, and whatever fluctuations are happening inside it, that is what is giving you the thermal entropy. So because there is not enough states at low energies, they are basically not back reacting or creating a black hole or anything. So so it's basically a thermal gas of gravitons in an ADS box. So
if we include the loop corrections from there, we will get a 0 plus some.
So I mean, what I was just saying that you need to include the loop corrections to get a non-vanishing answer. So because if you just did the leading calculation, you find the answer to be 0. But we know that there are these, in thermal ADS, the more better way to maybe say it is that the leading contribution is at order g Newton, which we have not computed, but there is no reason for it to vanish. Okay, so the leading calculation we did, and the leading calculation vanishes because the action is just beta times some quantity. Okay, so you can explicitly check it, but it's trivial to follow from the topology of the thermal ADS, right? So that's the statement. So the statement is that this is something that we have not calculated, but there is no reason to think that it is anything other than this. And to make our real statement here, this is all that is required.
And one more thing, like in the beta grid, if I replace the beta grid in the
thermal radius
Uh-huh.
action. So is there, what is happening there is it like the action of that thermal radius is becoming equal to the action of the large radius at that time.
Exactly.
And then it is
Yeah. So that's the place where both of them match. Yeah. So any other question? Okay, so how much time do I have? Half an hour. So we start at 10:30, right? Yeah. Okay. So what we can do? Yeah. So yeah, that's so the if you could treat it that way. See, the point is that Minkowski, like none of these things are super well defined, right? You could do a subtraction and do this calculation. Minkowski by construction it is 0 because we did a background subtraction to define it. So in that sense, it's not very interesting. You know what I'm saying? Here we are not getting a finite answer. Even for the ground state or the ADS case, because we are doing it in a more systematic and natural way, which involves this counter term. So in flat space, it's less clear. So also at the fundamental level, there is also another, which I said earlier already, which is that the black hole is never, So in some sense, you could even take the point of view that the vacuum is always the thermal, but the graviton, gravitons around flat space is the dominant phase, always. Because there's also a question of time scales here, right? So when you say that something is truly dominant in the canonical ensemble or something like that, what it really means is that if you wait infinitely long time, this is the dominant phase. At the end of evolution, finally when everything has settled down and you are truly approached the thermal state, this is the thermal state. So if you have, if you put a flat space with a cutoff in some way of regulating and so on, it seems like the natural thing is that gravitons are the gravitons or radiation that is left at the end of Hawking radiation is the natural final state. So that's sort of the thermal state, if you like. But you have to regulate the boundary in order to make that statement. And it's ultimately, in my opinion, it's related to the fact that it's an infrared regulator, so as I mentioned last time. So that's, I think, an important difference. So, and here on the other hand, things are much more cleaner. Because you are like, all these things that I said, this counter terms, etc., there are various nice matches with CFT renormalization type of stuff. So, so it's all very, very robust, and we didn't do anything shady. So, and the answer that we are getting is somehow nice and natural. So, yeah, so I don't know. Sometimes when I hear a question, I take off on a tangent and say something. Did I answer your question? Yeah, so I think so. I think that it's like a kind of because without a cutoff, it's not so easy to make sense of it, right? So, but so see, let me put it this way. So I think that nobody at least who is into who does string theory will disagree with the statement that 10-dimensional flat space is a truly stable vacuum of string theory or quantum gravity. That I think most people will believe. I don't think that anybody would disagree with that statement. So if you have a 10-dimensional black hole, it can evaporate, and ultimately what you will get is a gas of photons or gravitons or whatever in empty flat space is the natural picture. In 4 dimensions, we always have other questions. Like, for instance, how did you get this 4-dimensional space, right? So that kind of questions can arise because we don't really have a completely satisfactory description of full quantum gravity in flat space. Right? So, and then there is all these questions. But it might be the case that in 4 dimensions, completely in 4-dimensional flat space, you can answer some of these questions. But there are various trade-offs, and I don't want to make a very committal statement, So, okay, so but let's come back to this. Many of these subtleties may not, it's not even clear whether they're very important. I'm just saying that I'm not, what is the answer is not very clear. That's all I'm saying. So, okay, so what is the picture from the gauge theory side is the question. And this is, now we are coming into ADS safety. All of this calculations is essentially done long ago. So the claim is that this is related to what is called the confinement-deconfinement transition. In the gauge theory, okay? So the idea is that at low temperatures, order 1 degrees of freedom. So idea is basically that, like I'll give you an analogy with QCD first, but the QCD analogy is not completely correct. Okay, so the QCD, what you expect is that at high temperatures, QCD has, if you increase the temperature at you produce this quark-gluon plasma kind of stuff, right? So confinement is basically the statement that the degrees of freedom look like they are, the color degrees of freedom are separated. That's what it really means. But it should not be confused with the absence of gauge invariance. The degrees of freedom are still gauge invariant. This is a very important point, which is that even then, even if your quarks you can separate, it just means that there is enough energy to separate them to give, there is a Wilson line that you can use to connect between them. So there is enough energy to connect, energy in the system to create this Wilson line. That's what it really means to say that the system, this is the deconfined phase. It should not be confused with the statement that when you say that there are order n square at low T and order 1 at low T and order n square at high T, the statement is not that suddenly the quarks and gluons are just sitting there by themselves and there is no need for quarks and gluons by themselves are not gauge invariant operators. So you will still not be able to see them. They are still not gauge invariant meaningful quantities in, for instance, let's say gauge theories. But the point is that you can connect, the mesons are such that the Q and Q bar are far away. That's the way to think about it, so that there is enough energy and the Wilson line connecting them to make the system gauge invariant. Now the natural operators of the theory are known local operators. That's what it really means. Okay, so this is sort of what one would expect, very crudely, just from our what is it called, QCD intuition. So, but the point is that one big difference between QCD and the discussion that we had here is that QCD discussion about confinement, deconfinement is at infinite volume, which means we are essentially working with RD, not SD times R. Okay, so. So there is no natural, as it stands, if you look at just this, you might think that there is no scale. But QCD has this property that there is a new scale that is dynamically generated called lambda QCD. Okay, so that's around 200 MB for physical hour QCD, and this scale is what gives rise to the meaning, gives meaning to the statement that there is some notion of low temperature and high temperature. Okay, so if the theory, so classical QCD, classical, at least Yang-Mills theory, I don't want to talk about QCD directly because quarks have mass and there is some sense in which they have scale. But if you're just talking about classical Yang-Mills theory, there's no scale. Okay, so the QCD, the mass of the quarks is not what really is affecting the confinement scale. So you can, for all practical purposes for this discussion, you can treat them also as massless. So, and in that point of view, any temperature, any finite temperature is the same as any other temperature, you might have thought, right? Because there is no scale in the problem. So there is no, the only way we can say something about large or small is if there is some notion of dimensionless number which is large and small. There is no such number. If you just have finite temperature, all temperatures are the same. The only difference is between 0 and finite. There's no difference otherwise. So, but because of the presence of lambda QCD, then you have a dimensionless parameter which is T by lambda QCD. And then there is a notion of, T by lambda QCD being much less than 1 or order 1 or much bigger than 1. Okay, so, and the claim is that QCD, and it's a very complicated process in QCD. Again, QCD, the confinement is a very complicated process. We don't fully understand it still. But it's the general idea is that when T is much smaller than the QCD scale, okay, the temperature is small, the states that you find in the spectrum are basically the mesons and baryons, which are colorless, or glue balls, which are also colorless. Okay, so that's the picture that we expect from here. So the idea here in our, in the case of n equal 4 super Yang-Mills is actually more, it's a little bit more interesting, or it's, in some ways of looking at it, it's a little bit less interesting, because it is actually a truly conformal field theory. You know what I'm saying? The reason why in QCD had this lambda QCD is because in quantum corrections generate this new scale. And this is the process I'm sure you have, if you have taken a standard model course or something, you would have heard about dimensional transmutation, right? So that's the reason why there is a new scale that showed up. So initially you didn't have any scale in the classical theory, but quantum corrections generate a scale. And so this scale is a fundamental property of QCD and you have to measure it. You cannot, there's not a you can predict it from anything. So this is a number. In QCD, physical QCD is around 200 MeV. Okay, so So the point is that, but the point is that, but classically it was conformal, and that's why we initially had only a notion of finite temperature versus zero temperature. But this is literally the case in conformal field theories. So conformal field theories are truly quantum scaleless theories. So there is no scale. So then what are we talking about, right? So then there is no notion of high temperature versus low temperature, or the scale, there is no notion of phase transition at large t, because all finite t's are the same. So but that's where the sphere radius is super important. Because we are put not the conformal field theory not in RD, but we put it on SD times R, where SD has a scale which is controlled by capital L. Okay? So what we mean by large versus small temperature is basically that. So that's the thing that fixes, that's the thing that fixes, that's the thing that gives you a notion of high temperature versus low temperature. Otherwise we would not have such an idea in a conformal field theory. And that's the answer to why we don't have a Hawking-based transition in Poincare patch. Okay? So if you have a Poincare patch, the boundary is Minkowski space. There is no real scale there. Okay? So, but on the other hand, if you have a sphere, it's a compact space. That's the more correct way to say it. Because it's a compact space, there is a sense in which there is a natural scale. That one can associate to it. Okay? So, okay, so so that's one statement, and okay, so let me just say a couple of words about. So there is a notion of this is, I think it's good to hear it. So even though it's not super important for us, which is that. So phase transitions are usually characterized by what quantities called order parameters. So order parameter is just basically some core expectation value or some parameter, some quantity that you might compute, some expectation value ideally. So some expectation value which takes some value on one phase and some value in another phase. So that's called an order parameter. So if you can identify this value, then you say that you can recognize which phase you are in. So there is an order parameter for confinement, for this confinement deconfinement thing, and that's basically called the Polyakov loop. Okay, so this Polyakov loop is nothing but, should I write it? So if you have a gauge field, this is what I mean by the Polyakov loop. Okay, so so the idea here is, the path ordering and this thing, etc., don't really matter. The trace is because if I have a non-abelian theory, I need to have a trace. So none of this is, if you have not seen too much of Wilson loops, it doesn't matter. But the point I want to emphasize is that this guy is computed around the thermal circle. So typically this sort of a guy is typically called Wilson loop. So the reason why we are distinguishing and calling it Polyakov loop is because we are computing this circle, this A mu. So let's say your space is, so let me say the space is a little bit like this. Okay, so this is your tau circle. So I'm computing, this is my tau circle, so I'm computing this Wilson loop around the thermal circle. Okay, and the claim is that when W is equal to 0, we are in the confined phase. And when W is not equal to 0, we are in the deconfined phase. Okay? And the physics, the philosophy or the general idea why we think about it this way is because essentially a Wilson loop is what a charge will couple to. Right? So for instance, if you have if you're in yesterday's just in stock, he wrote down actions of this form. Right? So this is essentially the statement that the charge will couple to a Wilson line. Because that's essentially what a point charge is. Right? It's basically coupled to a world line and you're integrating over it. So what it is saying is that, so very crudely, I'm just giving a very crude reason to believe why this is the case, is that it means that free propagation is somehow allowed. You know what I'm saying? Free propagation, or the quark charges can freely propagate in this phase, and that's why this quantity is non-vanishing in the deconfined phase. Okay? Is that at least sort of plausible? What I'm saying is that if there is no charges, if charges are confined, then there is no notion of this quantity. This is essentially a thing that moves a charge around the thermal circle, right? So if this quantity had no expectation value, that means that the propagation of the charge around the thermal circle will have zero, it's basically, it's no expectation value, okay? So I have not quite explained to you why the thermal circle is important. That I'm not going to explain now. But the point is, at least it is plausible that it is, a finite Wilson loop like quantity expectation value is a reasonable measure of confinement versus deconfinement. Essentially why we are doing it in the thermal circle is just because that's a non-contractible loop, that's all. You know what I'm saying? Because the thermal circle is non-contractible. That's the only reason. Okay, so yeah, so this is what is called the, so why did I tell you this? Because the reason I told you this is because this quantity is actually, generally speaking, many cases it's not very easy to calculate in the gauge theory. But in the bulk, it's very easy to compute it, because if you remember, so that, the one case we have this kind of a geometry, and in the other case we have this kind of a geometry. Right? So in the global ADS or the thermal ADS, we basically had a circle times some kind of a cylinder, right? And here we had circle times it's essentially a disk. And the advantage of this is that in the ADS CFT correspondence, this quantity, the Wilson loop of the boundary theory, is naturally computed in the bulk side by using the world sheet of a string that ends on the Wilson loop in the boundary. Okay? And it is, here you can automatically see, without doing any calculation, you can see that there is a natural world sheet that you can write down here. This is the world sheet of the string. Note that it's a Euclidean world sheet. Okay? So that's why it's not propagating in Lorentzian time forever. This is a Euclidean world sheet, so it's basically like a cap. I mean, it's living here. Note that there are other directions here. We only care about T and R here. So here, on the other hand, you cannot do it. The string will basically, you can't have a world sheet of a string without specifying some other boundary conditions, maybe cutting the string, something like that. There's no natural, world sheet of the string that ends in this case. So this means that here we expect the Wilson line, not the Wilson line, the 't Hooft loop to be 0, because there is no natural string world sheet action that you can write down here. So the expectation value should actually be 0. You can make it more precise, but even just barely qualitatively already everything is clear, is my point. Here, on the other hand, you expect it not to be 0. Okay, so and that's related to the fact that this is the deconfined phase, this is the black hole, and this is the thermal ADS where it's confined. Okay, so that's a sort of so I'll say one more thing and let you go. So the final thing is that in a general conformal field theory, we expect, just on dimensional grounds, that the free energy, so the free energy, I think it's basically the action, I think. I mean, we can go look it up, but free energy is, so let me not sweat it in the last minute. We can fix it probably, but it's too much work right now. So this is v to the power t power d, okay? So this is, there is a minus sign also. Okay, so that basically means that t to the d is just essentially the Boltzmann factor, the Stefan Boltzmann kind of factor, and it has to go extensively. This is completely fixed by dimensional analysis actually, because it has to go extensively, and then the only other thing that it can depend on is temperature, and the dimensions will fix it to be t to the d. Okay, so this is the way in which you fix. This is a standard fact. So because we know that in the deconfined phase it should go like n square, we can also write this. Right? It's order n square. This is in the n equal 4 case. We expect that in the deconfined phase, the free energy or the action should basically go as n square. Okay, so that's what this n square is. So we are not fixing the overall factor, but this much dependence, this you can fix by dimensional analysis, and this you can fix because you are in the deconfined phase. Okay, so now you can ask this question: so this is in the strongly coupled limit of ADS CFT. So it's in very roughly speaking. So n is pretty large, and on the gravitational side, lambda is very large. Okay, so if you want to have a gravitational description, this is where the gravity calculation is trustable. So that's where we did it. Okay, so this is the limit. This is roughly the regime in which our calculation is supposed to be valid. So, and actually you can compare this with our the bulk calculation that I did. Replace all the relevant, V with L depending on the radius of ADS and all that. You will see that this actually matches. Okay, except that we will also be able to fix the coefficient here. So, but anyway, so the point is that this is the calculation that, this is the expectation in CFT. So, and this is where we actually did the calculation. Okay, so it turns out that this quantity in the other limit, you can actually compute it, where lambda is going to 0. Okay, because lambda is going to 0 is sort of the free limit of n equal for superangles at large n. Okay, free in the sense of Tooft coupling. So this is something that you have to be a little bit careful about when you're discussing these things or seeing or reading papers or something, because if you're in the standard quantum field theory textbook, we talk about G-square Yang-Mills as the thing that sort of controls the freedom. That's the coupling. Here, when we say many times it's a weakly coupled theory, what you really mean is the Tooft coupling. Okay, so but anyway, so the lambda equal to 0 limit, essentially the theory is free. That means that you can treat the, just consider the n equal to 4 super Yang-Mills theory, but forget about the fact that there is some, complicated action, you have to do various calculations, etc. You just treat it as a theory of free gluons, scalars, and fermions. Free, and there's no mass, there's nothing. So all the fields are free, and all of them are, you can just compute them using free, free scalars, fermions, and gluons. Well, how would you do it? You can compute it. The calculation is not completely trivial because you also have to demand gauge invariance, but it's manageable and it's doable. And it was done in great detail by, for instance, Shiraz and company back in, at the time when I was starting my PhD, roughly speaking. So maybe a little bit later. So. So yeah, so this result is easy to compute, or easy, or at least it's doable. And in the lambda, strict lambda going to 0 limit, actually many things are, it was done even before. You know what I'm saying? So, and the result of the free energy, let me just write it, is, so I'll write it as this. F has to be of the form F lambda pi square by 6 n square t to the 4, where F of lambda is some unknown function. Okay, so and the claim is that f of lambda at lambda going to infinity is 3 by 4 and is equal to 1 when lambda is going to 0. Okay, so this calculation is essentially what we did. Okay, I did not write it in terms of, did not translate the G Newton and so on, but you can rewrite it in this form in the limit when the sphere size is becoming large. Okay, so this is the gravity calculation. Okay, that corresponds to lambda becoming very large because that's the supergravity limit with weak Newton, G Newton. So this, on the other hand, is the result of just treating it as a free particles and just computing the free energy. This is something that we can do in quantum field theory. And the result is 1, and this is 3 by 4. And this 3 by 4. So, but so this paper was written by Gupser, Klebanov, and Peat. The P, there is this combination seems to be like a magical combination. So this is, there is this time it's the P is different, but so this calculation was done, in 1996, and Maldaceno's paper was in 97, and the observation. A version of this calculation was done, and the idea here is that you are going from, you're tuning your coupling. So there's no supersymmetry to protect anything. Okay, so this variation in this result is not, it's not. We are not expecting it to be 1. You know what I'm saying? But at the same time, it is very striking that the same result was obtained by gravity, but almost up to the same factor. It's an order 1 number difference, right? So this was considered to be a remarkable, and I think that this must have kind of helped Maldaceno to think with his, how he approached the problem. But so this is an old result. Right before, a year before ADS-CFT was discovered, it was noticed that it is the case that so they phrased in terms of D3 branes. So the D3 branes in the free limit of n equal 4, you compute it this way, and in the other limit you compute it using the black brane metric, and then you find, which is essentially what we have done, but in a slightly different way. So what we did can be closely related to it. So yeah, but this precise factor, yeah, I don't know whether it's precise factor we will get. We may get it. So, because they are doing the calculation in D3 branes. But anyway, so this is the gravity calculation, which is doable, and you have a result, and this result is also there. So this is sort of like an interesting renormalization group running, here it's the running of some quantity with the parameter lambda as you are changing your lambda, right? And you can see that, and it's interesting that it's close enough. And yeah, I just thought I'll mention it because it is also mentioned by Hartman, and I thought, yeah, I think I'll stop here. Any questions?
So lambda tending to 0 is the boundary limit of the
No. So lambda tending to 0 is the limit when the gauge theory is free. So the n equal 4 super-Yang theory is free. So that has nothing to do with the bulk, this thing or anything. For any given lambda, there is an entire radius space-time sitting there. For any given value of lambda and n, the dual theory is supposed to be a quantum gravity. So, but the point is that it will have a semi-classical Einstein gravity type of dual when n goes to infinity and lambda is large. Okay, so that's the statement. So, but at finite lambda, when lambda is really small, this is precisely the opposite limit. Okay, so lambda is very small means this is in some sense, very sort of stringy kind of limit, if you want. So, yeah.
But see, closing the bulk is related to the fact that quarks are interacting.
Quarks are what?
Quarks, but see, it's closing in the bulk. Can you say the quarks, there is an interaction between the bulks?
It's I don't know whether that's a good way to think about. Maybe, see, the point is that the quarks are sort of like boundary things, right? So these are open strings. The way to think about them is they are basically open strings which are attached to some boundary, and this is like roughly like some particular configuration, and this you can calculate using world sheet string theory. So you can calculate using what is called the Nambu-Goto action. So I don't know whether it is interacting is it's not so much interacting, I would say. It's more like, yeah, I guess you could say it's an interaction in some ways, because you're computing a one-point function for the quarks, or for at least for this Wilson loop type thing, and you're saying that it is it's non-vanishing. So it's some sort of an interaction with the background of this guy. So maybe you could say it that way. Yeah.
So in this second case,
yeah. It's not that there is, so better to say that we are there is no way to have a free quark in the system, right? That's more the correct way to say it. So here, for instance, so note that these quarks that we're introducing are in some sense probe quarks. These are not part of the theory itself, because the theory doesn't have, they're all adjoint fields. Okay, so but you are adding these quarks to the system as a probe of how the system might interact with you. So in that sense is what I'm saying, that there is some kind of an interaction with the system. We are coupling it, but I don't know how useful, or I don't know whether that's the best way to think about it. But I'm just, yeah. So below this temperature, the quarks are there. The quarks cannot be free. Free quarks cannot have any expectation value. Free quark propagation cannot have any expectation value. So yeah, I don't know. I don't have a more. Yeah. Any other question? You got a question? No. Okay, so I think we'll stop here. So so I think this is sort of like a broader review of ADS-CFT still, I would say. But I think now we will talk about information paradox. Try to get into information paradox. I don't know how many more lectures we'll need. You can turn it off, it's fine.